Good morning to everyone. It's my pleasure to be joined to my right by Chairman of the MTA, Fernando Ferrer. To my left, Mary Boyce, who is the Dean of the Engineering School of Columbia University. To Mary's left, Lance Collins, who is the Dean of the Cornell School of Engineering, and they'll introduce their colleagues as they go. We're also joined by Andy Byford and Pat Foy and Ronnie Hakem, and I want to thank them for their attendance. Special thank you to our special guests who have worked very long and hard and pro bono, but they've done an extraordinary job. And to the members of the press, go easy on our special guests. They are not accustomed to this. President Obama once said that the issues that come to his desk are the hard issues that make a major difference. The easy issues get solved by someone else. So the ones that tend to come to the president's desk are the really difficult ones that have a high level of impact. On a much lower scale, the same is true for me as governor. I tend to focus on the issues that are highly impactful, right? So whether it's new Moynihan train station, second and third track on Long Island, new Javits Center, subway action plan, major projects that make a major difference in people's lives. Prison breakout at Dannemora. I just saw the movie the other day on TV, so I'm thinking about it. Michael Imperioli played me. I thought he did a good job. My daughter said that she thinks I'm better looking than Michael Imperioli. She said it at the same time she was asking me for money to buy a gift for her boyfriend, but I'm sure they were totally coincident, those two facts. The L train is one of those issues. I can't tell you how many people have approached me about the L train and the difficulties that the L train closure would trigger. Now, the MTA has done a very good job, the city's done a very good job in trying to alleviate the problems with the L train closing. And a lot of people worked very hard, and I applaud them. But the simple fact is you have roughly 250,000 people who would need another way to get to work. That is going to have a tremendous impact on traffic, et cetera. 15 months. Sounds like a relatively short period of time. It's not if you're doing it one day at a time trying to get to work. So what I did was I asked a panel of the best experts we could find with a set of new eyes to come look at the L train situation. With no predisposition. And I asked, review the plan, look at it with fresh eyes, no assumptions, no givens. If you have any positive suggestions as to how we could make it better, great. If you say they are doing it the best way possible, that's great too. But I want to be able to say to the people of the state, we have reviewed it, we've looked at it, we've scrubbed it. I had the best experts on the planet look at it, and this is the best way that it can be done. That then started a series of discussions and meetings where the Cornell and Columbia team needed to be brought up to date. We went through the tunnel. which is always a fun experience, especially in the winter. We went through the Amtrak tunnels. We talked to everyone there was to talk to. I educated myself to the best extent possible. And that was their challenge. Is there any better way to do this? Make a long story short, they have proposed a new design to use in the tunnel. It is a design that has not been used in the United States before, to the best of our knowledge. It has been implemented in Europe. It has never been implemented in a tunnel restoration project. They came up with that design suggestion. It uses many new innovations that are new to, frankly, the rail industry in this country. But the MTA has gone through their recommendations and gone through the new design, and the MTA believes that it is feasible. It's highly innovative, but that it is feasible. Long story short, with this design, it would not be necessary to close the L train tunnel at all, which would be a phenomenal benefit to the people of New York City. There would need to be some night and weekend closures of only one tube, so service would still work because there are two tunnels. But it would be a major, major breakthrough. And that's what we want to discuss with you today. Just to give you a little bit of the context, because I know while many of you are familiar with tunnels and tunnel construction and tunnel design, I know Zach Fink, before he became a reporter, actually studied tunnel design in Europe for many years. But besides Zach, I want to give the others of you a little framework. The L train tunnel, as you know, it's about a mile and a half long. It's over 100 years old. It goes from First Avenue in Manhattan to the Bedford Station in Brooklyn. The tunnel goes from Manhattan to Brooklyn, 7,900 feet. The tunnel itself, 7,100 feet. 2012 Hurricane Sandy, which is caused all of these issues. Gateway Tunnel, Hudson River Tunnels, Montague Tunnel, L Train Tunnel. What's the common denominator? It is the first time you had a tunnel that was filled with salt water. That does not happen. That has not happened. Queens Midtown Tunnel, Brooklyn Battery Tunnel, same thing. It's been an entirely new experience to have a tunnel filled with salt water. And that's what Hurricane Sandy did. And that is much of the reconstruction that we are now doing goes back to Hurricane Sandy. The major structural elements of the tunnel are fine. There is no structural integrity issue for the tunnel itself. So people worry, is the tunnel going to have any significant issues? No. The structure of the tunnel is fine. The issue is the saltwater intrusion coming into the tunnel, which then made contact with the electrical components in the tunnel. And that is the problem. Salt water and electronics do not mix, period. It is a toxic combination. And it's not that the water comes in and the water goes out and everything is fine and you dry it. The salt remains, and the salt remains in places where you can't get it out. So circuit breaker boxes and the power cables. You'll hear a lot about the power cables. The power cables are the cables that power the train. And they are very, very important. They were all exposed to salt water. That was an accelerant for the corrosion. That's what has created this entire situation. You'll hear about the bench wall. What is a bench wall? The bench wall are walls that are on both sides of the tunnels. You can see them from the platform, a subway platform. It's where a worker would walk out into the tunnel. You walk along the top of the bench wall. And the bench wall often has a railing on the outside or on the inside. But it's the walkway that you walk out into the tunnel. The bench walls are about 2 feet wide. They're about 50 inches high, and they're all cement. The bench walls also are very important for the power system of the tunnel, because the bench walls maintain and hold the power cables are within those cement bench walls. They are also practically a walkway for workers to go out and, in case of an emergency, access or egress. Why did they put the cables in the bench walls? Because remember the initial design, this is 100 years ago, they needed fire protection for the cables, and the cement provided fire protection for the cables. So they literally ran ducts, pipes in the cement. Within the duct or the pipe, they ran the cable. And then they entombed it in cement, and all you see on the outside is the bench wall. So that is the bench wall. When you're riding in a train, you see the bench wall. This is a bench wall that is crumbling. The bench wall in the L train tunnels, in some places it's intact and fine. In some places it is slightly weakened. In some places it is crumbling. The places where it's crumbling are the places where the salt water was the highest and remained the longest, because the salt water got into the cracks in the bench wall, and the salt sat and the salt deteriorated the bench wall. This picture, you can see the pipes in the bench wall. Within that pipe is the power cable. Okay? That's the way they did it. The current plan was remove the entire bench wall, remove all the conduits, remove all the cables. That's 32,000 feet of bench wall between the two tunnels. Install all new cable, and then rebuild the bench wall. That was the plan. It was labor intensive because much of the bench wall had to be removed by hand. It's a 100-year-old tunnel. You're taking out a cement structure attached to the lining of the tunnel, so it would have to be broken up by hand and removed. I'll start where I ended. I asked Columbia and Cornell to assist the state of New York as good citizens of the state of New York. They agreed. The dean of the engineering school of both Columbia and Cornell put together teams, went through the whole process, went through the tunnels, and I said to them, any new idea, outside of the box, creative, any way to reduce the 15 months, we are open. Let the MTA say that's an idea that just is beyond reality. Or confirm that this is the best way that we can do it. So I have confidence in saying to the people of New York, this is the shortest, best route to the rebuilding of the tunnel. Again, I want to thank them for their work, because they did work very hard. They've all mentioned individually that I was a pleasure to work with. Slight editorial comment. But with that, I'm going to turn it over to Mary Boyce to walk us through the first part of the program, and then you'll hear from Dean Collins, but first we'll hear from Dean Boyce.
Okay. So thank you all for coming to hear our story. First, I want to, on behalf of both the Columbia and the Cornell teams, to thank Governor Cuomo for inviting us to participate in looking at the incredible challenge, and rather unique challenge, as you've heard, on how do we address the L train tunnel. And recognizing there's been a lot of work done before, but how can we come and give a new look to this problem in collaboration with MTA and others. We realize what a privilege it is and an honor to be asked to serve in this capacity, that this impacts hundreds of thousands of lives of New Yorkers, and many of us on the team are New Yorkers too. And also the impact on so many businesses. So we do appreciate the gravity of this task. So when we look, let me first introduce our team. As you've heard, I'm Mary Boyce. I'm Dean of Engineering at Columbia University. I'm a mechanical engineer. Lance Collins is Dean of Engineering at Cornell University, also a mechanical engineer. Andrew Smith, a professor of civil engineering at Columbia University. Tom O'Rourke, a professor of civil engineering at Cornell University. Peter Kingett, a professor of electrical engineering at Columbia University, also chair of the Department of Electrical Engineering. George Diodatis, a professor of civil engineering at Columbia and chair of the civil engineering department. So we've actually, over the last 3 weeks, literally spent hundreds of hours collectively working on this project. As you've heard, we've toured the L train tunnel. We also toured the Hudson River tunnel, the Amtrak tunnel. I also want to say what a collaborative effort this has been, that we've worked very closely with consulting firms, WSP and Jacobs, and various contractors, with very closely with the MTA and New York City Transit. This has been an incredibly team work-focused collaboration and very productive. In particular, I do want to mention three people who led different teams: Pat Foy from MTA, Charlie Hall, and Jerry Giannetti from WSP, and their entire teams have been so instrumental in all that we've done. As part of our review, we did look at what are some of the designs and systems used in more modern tunnels across the world, to see what we could learn from those practices. As was mentioned, some of the tunnels we looked at: London, Riyadh, Hong Kong, also Singapore. That one of the things you've heard about the benchwall. You're going to hear a lot more about that in a few moments. But we have found that in newer designs, the cables are not placed within bench walls, right? Also, if you can get a little bit of a look at these tunnels, cross sections, you also see that there's a lot more space around the train in these newer tunnels, right? So that's also an important factor. So let me start with the recommendations. So our recommendations, while we're going to go through them in a little bit of a linear fashion, are really a result of looking at a highly integrated system of bringing together emerging and new technologies from little bits and pieces from many different proven technologies that are out there. And these have led to our primary recommendation that we recommend implementing a new way to do the power, control, and communication systems, and how to embed these in the tunnel. So the tunnel cross-section you're seeing here is the L-train tunnel cross-section. So within that, not to bore you with all the details, but as engineers, we can't help ourselves sometimes. That you can see the cross-section of the train, and you also see this yellow envelope, and that's kind of the keep-away envelope, meaning that everything outside the yellow envelope and within the walls of the train is the space that we have to work with. So this is another challenge. It's a highly tight space, highly geometrically confined area that we get to work with. So you can see why cables are in bench walls in a tunnel like this, right? Because they fit, okay? And they get protected and all of the other elements that you've heard. But we said, let's not be confined by that. Let's think more broadly, right? So I'm going to focus first on the cables, and then I'll hand over, and Dean Collins will talk about the details in the bench wall and others. So we're going to we are recommending that the cables be racked. Okay, so the majority of the cables, the power cables, the communications cables, control cables, these power the train, the pump, the fans, that these be racked along the walls on one side. This leaves the other side free for egress and access. All right. So, and we have looked at many challenges with actually doing this, and different ways to actually rack these cables. And we have found that it does indeed seem to be possible. We will also place the negative return on the track bed. So what this is essentially doing is decoupling the cable system from the bench wall, right? These are two different functions. We're able to execute all of the functions of the cables without them being in the bench wall. So we do not give up or sacrifice any functionality of the system, right? An important thing that we have to address is making sure that the fire retardancy is still possible for these cables. So the cables must be jacketed, and they're jacketed with a low smoke, zero halogen, fireproof material. Okay, and this is a proven technology. It has been used in these newer designs, in newer modern tunnel systems. It's also used in aircraft, right? And so what happens with these jacket cables, okay, is that yes, there's some sort of thermoplastic or thermoset, but they have an inorganic filler so that they char in the presence of heat or fire, and so there's no outgassing, and they actually become even better insulated. So this is another key feature of being able to rack these cables on the wall and not embed them in the bench wall. This also very importantly means that we can abandon all the old cables in the bench wall, right? We do not need to remove them and replace them. We just leave them there. So if a bench wall is still structurally sound, we do not need to destroy it and remove the cables and rebuild it. Okay? This is a very key factor, okay, so because it significantly reduces demolition and construction, and we feel probably has a cost implication as well. Okay, I'm going to now hand this over to Dean Collins, who will talk about the bench wall.
Thanks, Mary. Let me also add my thanks to the governor for giving me an opportunity to work on this project. This has been an incredibly exciting 3 or 4 weeks that we've had a deep dive and have learned a lot about the Canarsie Tunnel. So I'm going to pick up the conversation from where Mary just left off and talk a little bit about the bench wall. As the governor mentioned in his opening remarks, we're going to place the bench wall into 3 categories. So there's bench wall that's going to, in some sense, be stable and will remain. There's bench wall that's been compromised to some degree, but not significantly, that we think we can reinforce using something called fiber reinforced polymer. So it's essentially a mixture of epoxy and fiber to wrap around. And if you look at the figure to the right, you'll see essentially wrapping it around the bench wall and strengthening the bench wall. This will last for decades, you know, for a long period of time. It's not a quick fix. It's technology that's been widely used in bridges, in buildings. So we're simply applying it in a very different application here. And then there's a third category, which is bench wall that really is just not structurally sound, that has to ultimately be demolished and removed. Then the question becomes, how do we know what's what? And so we're going to use a state-of-the-art ultrasound technology to evaluate the entire length of the bench wall and figure out, you know, which parts of the bench wall are in which categories, and then and act accordingly to either leave it as it is, or to reinforce it as needed, or remove it as needed. And what's important is that the bench wall is really serving the primary purpose. It's back to its primary purpose, which is access and egress. It's no longer serving any role with respect to the cabling, and so that's the only element that we have to ensure in terms of functionality that we have retained. In addition to this, one of the concerns that you have is, well, the bench wall at one period of time may be in one state, but it may deteriorate over time. How will you know if that's happening? And so, in addition, we are going to install smart fiber optic sensors. These are sensors. It's a fiber optic cable that will run along the vertical side of the bench wall, along the length of the tunnel. And these sensors will be able to pick up small changes and deformations in the bench wall in advance of failure, so that if there were something that eventually is going to fail, we'll know that in advance and be able to send in a team to go in and do whatever's necessary, reinforce that section as needed in advance of the actual failure. So this is really state-of-the-art technology. It's been applied in new tunnels. This is an unusual application in that we're applying it in as part of a rehabilitation of an existing tunnel, but it's proven technology. And so I think that the fact that it's proven technology means that it will work beautifully here. But we're not going to just stop there. So the other thing we're recommending is that we introduce a LiDAR system. What LiDAR does is it essentially maps out the shape of the tunnel at a given instant in time. This is not going to be continuous monitoring like the fiber optic cable. In this case, this is going to be something that we would mount, for example, on a train. And as the train is passing through the tunnel, it would do a reading of the tunnel. So it would be sort of periodic. But it would add a second and a complementary evaluation of any sort of deterioration that might be going on within the tunnel. So with these two pieces of technology, we think we will be able to know in advance if any section of the tunnel is showing signs of deterioration, and be able to head off any more significant things that might happen. For example, if there were sort of structural loss and into the actual train area. So both of these are, as I said, state of the art, and we feel, but on state of the art, but on the other hand, proven. And I'll just mention that this is the baseline of what this technology can produce, but there are constant advances that are going on with the technology. Once deployed, we will continue to try to get more and more additional information from the signals coming out of those cables. So, for example, the cables can pick up vibration. So as trains are going by, we would be able to see if the vibration signature is changed over time. And that may indicate sort of problems that may be going on, not in the bench wall only, but also in the track system. And so there's not only the sort of the immediate benefits that we see happening, but in fact, over a longer period of time, and as the sophistication of this technology grows, even higher level understandings about the operations that are going on within the tunnel. Of course, we've removed some of the bench wall, and so we're going to have to install a walkway where the bench wall no longer exists. We imagine that this could be just fiberglass, steel. It would be relatively simple installation, certainly a lot less expensive than reconstructing the concrete bench wall. So we see a savings as far as that's concerned, but we would still have a pathway from the standpoint of access and from the standpoint of egress and from the standpoint of safety. We also looked very carefully at the resilience. This is not going to be the last, as bad as Sandy was, it's not the last storm that New York is going to experience, and so we wanted to make sure that the tunnel is more resilient than it was before. We're making 4 recommendations to improve the resiliency of the tunnel. The first is that we want to increase the pump capacity for the tunnel. So as it currently stands, there's a single drainage pipe. And we will have, in fact, now drainage pipes that will run to the Manhattan side and to the Brooklyn side, so that we can double the amount of water going through those pipes. In addition, we've increased the pumping capacity of the standard pumps and of the emergency pumps to dramatically increase the amount of water that can be pumped out of the tunnel during under emergency situation. The second thing is we looked at how those pumps are powered. Obviously, they only run if they're going to be powered. And so there are utility lines that are going to run from Manhattan into the pumping station and from Brooklyn into the pumping station, providing one level of redundancy. So if one of the grids goes down but the other grid is up, then the pumps are continuing to run. In the event that both of the utilities go down, though, then you need to think about an external generator to provide that power. So we are recommending that a permanent generator be installed. Moreover, we would like to explore the option of possibly powering that generator using natural gas rather than a diesel fuel. The advantage of having it powered by natural gas is that the emergency generator would be able to run indefinitely, so it would not stop running when the diesel fuel, as it would with diesel fuel when that ran out, when the tank ran out. And of course, under conditions that we're talking about, it's sort of a major storm is hitting, there's just a lot of things going on at the same time, and so the notion that this external power would be there indefinitely would add certainly to the resilience of the tunnel. Third is that we, and there's a demonstration of this shown here with the Queens Midtown Tunnel, the consideration should be given to potentially putting a watertight gate on the 2 ends of the tunnel to protect the tunnel from any sort of major flooding. So I'm showing an example here of in front of the Queens Midtown Tunnel. The Brooklyn Battery Tunnel has something very similar, and so there should be some consideration given to that. So that's our third recommendation. And fourth, there's a lot of vent shafts and so forth that run along the entire length of the tunnel. That's where the water is going to get in, and so we're recommending that all of those openings, that some sealing facility be sort of built into all of those between the First Avenue station and the Bedford Avenue station, especially all of those that are under some critical elevation. And so that should be something that's examined and implemented as needed. And finally, I just wanted to point to the fact that public safety was always in our mind. It was in every conversation that we had. And there were really sort of 2 aspects of it that we discussed at some length. One had to do with the actual construction project, and one had to do with the operation of the tunnel after the construction. So during the construction, the demolition of the duct banks and the removal of the duct banks is going to generate a good deal of dust, and importantly, airborne silica, which is a hazard for humans. And so part of what the construction company will have to do is monitor that and ensure through filtration and remediation that the air has been cleaned before that tunnel could then be reopened. So we made an additional recommendation beyond just having the company itself monitoring, but there should be an external independent evaluation and monitoring of air quality to ensure this is sort of public assurance that that in fact the air quality is as is needed. And then in terms of the ongoing operations of the tunnel, as already mentioned, we're recommending this smart technology be introduced. This will monitor the structure of the tunnel. This is in some sense raising the quality of safety within the tunnel even beyond what it is today by introducing this technology. And so we conclude that in a sense we're leaving the tunnel safer than it was originally. So let me just quickly run through those all of the recommendations that are being made. So we start with a new power and control system, as was stated, and in fact implementing a racking system for hanging the cables outside of the bench wall. This decouples the cables from the bench wall and allows us to then treat the bench wall in a somewhat simpler way, and not comprehensively remove all of it, but in fact only remove that portion that is needed. We want to jacket the cables with a fireproof material that is also low smoke, so that in the event of a fire, people are safe. We'll abandon the cables that currently exist within the bench wall. There's no environmental concern there. We will leave the structurally sound bench wall in place, reinforce the less structurally sound bench wall, and remove the unstable bench wall. Number 7, we'll install a smart sensor system that is state-of-the-art to monitor the structures initially, and ultimately, I believe, the operations within the tunnel. 8, install a walkway so there continues to be a pathway for access and for egress under emergency conditions. 9, install and improve the resiliency of the tunnel in terms of any future storms that may be coming along. And 10, as I mentioned, we always had public safety in mind as we went through this exercise.
So to quickly summarize what are the benefits from this, first we see that the new system design is a highly integrated design, and it achieves all functional outcomes. And at the same time, it's reducing the work and this is happening because it allows some simultaneous and not sequential execution of the critical elements. Importantly, because we are racking the cables, that the old cables remain functional while we're actually placing the cables. And this is an incredible process change, which is what leads to the outcome of no closure, which was preempted by Governor Cuomo. The racking system allows greater access to the cables for inspection and future upgrades. So as we have newer technologies arise over the coming years and decades, we will be able to replace and upgrade much more easily than if these were embedded within a bench wall. The installation of the smart sensor system allows for the monitoring of the bench wall, but also, as you heard, other aspects of the tunnel and the train system on a continuous basis. This is actually helping bring us in to usher in the era of big data as part of actually monitoring and knowing what's happening in our tunnels. Okay, this will create a state-of-the-art capability here in New York. The upgrades to the pump system and the rail can occur in tandem. These were planned, and they can occur in tandem with the cable and bench wall work. Okay, so there's no compromising on those upgrades. And we see a dramatic reduction in what we refer to as the non-value added project scope. So we don't reduce the scope, but we eliminate those parts of scope that had no value. For example, if we do not need to remove the bench wall and reconstruct the bench wall, we're not going to do it. And that's an incredibly time-intensive, labor-intensive element that we remove. It had no real value when we do not need to do that, so we leave it in place. We also see that we have enhanced safety and functionality of the project and of the end experience for every commuter. And we have enhanced flood resilience. We also think this positions New York to be a leader in infrastructure, right? This is, as we all know, a unique situation. We have a 100-year-old tunnel that was damaged by a flood of unusual circumstances. This actually gives us that opportunity to be innovative in how do we really do the right next new thing for the long term. And we think that another added benefit then is that our success here can be mapped onto other systems here in New York and elsewhere. So we have projects underway and the plans, the Second Avenue Phase 2, the Hudson River tunnels, and many other places where we'll be able to deploy some of the unique aspects of this very integrated design, which pulls in emerging and new technologies that have been proven elsewhere, but have never been integrated together and used to restore and rehabilitate a 100-year-old tunnel. So as you heard, what this means ultimately to New Yorkers, okay, to businesses, is that no closure of the service is necessary with this new design. We feel strongly that this is possible to execute this system design without full closure. The work can be completed with weekend and nighttime closures, and doing so one tube at a time. So this leaves one train always available to do the back and forth when one tube is being repaired. I'd like to further emphasize, this has been a highly collaborative process. We've benefited so much from work that was done before, but also so much from the collaboration over the last 3 weeks with our partners, the consultants from WSP and Jacobs and from the MTA. We have presented this to the MTA, and we feel confident that they will be able to implement this, and I think we'll be hearing from the MTA next. Maybe before we move to the MTA, if any of our colleagues want to,
if you don't mind, I'll turn it over to my colleagues in a second. I just wanted to add my thanks to all of the MTA and the consultants. In 3 weeks, I don't know how many dozens and dozens of questions we asked, and each it's literally hundreds. And we can say these words, the kind of high level statement about putting up racks and hanging the wire, but what really you have to do is you have to do that along the entire length of the tunnel, and there are tricky areas that have to be worked around, and there were lots and lots and lots of questions. And I was incredibly happy to see their willingness, day, night, weekend, Christmas Day, New Year's Day, to lend a hand to help us to understand a particular issue. And so it just seems appropriate at this point to say a genuine thank you to all of them.
Yeah, so, and I'd say that the level of detail behind each recommendation and the background work needed to say, do we have confidence with this recommendation, is really incredible and could not have been done without the consultants and the MTA. It has been a very much a team effort and highly collaborative, and I would also say that we never got a single bit of pushback with any question we asked. Anything we asked was addressed, which I was really such a welcoming, collaborative spirit. I think we would like, if our colleagues have anything they'd like to comment on. Tom?
If I could, I'd like to emphasize what an extraordinary opportunity the rehabilitation of this tunnel presents. Look, we're all aware in the United States that infrastructure is one of our major national challenges. Infrastructure is not only generic, but it's local. It's our infrastructure, and when it affects your community and it affects the people that you live with, and we have an opportunity to fix it locally and take a leadership position nationally and internationally, then we have a win-win situation. What we believe is that we have a design here using new technology, advancing new technology, particularly with the fiber optics and the combination with the LiDAR to be able to monitor in great detail the structural condition of the tunnel over time. We believe that this allows New York to take a leadership position in monitoring infrastructure and bringing more effective infrastructure to the people, not only in New York, but across the United States.
Something very quick. I fully agree with what my colleague mentioned and what the two deans mentioned. This is a truly unique opportunity for New York City and New York State to become a worldwide leader. And as already mentioned, the collaboration with the consulting industry was absolutely critical in the overall process. But I would like also to mention that without the invitation coming from Governor Cuomo, nothing like this outcome could have been possible. So everything started from the invitation of Governor Cuomo, and I would like to deeply thank him for this.
Anyone else? Colleagues? Okay. Before I turn it over to the chairman, necessity is the mother of invention. A closure of 15 months was highly problematic. Necessity is the mother of invention. What these people have designed is the first of its kind in the United States of America. No rail system has used this approach before. So it really is, from their point of view, exciting. I don't know if you can tell, but these are engineers excited. They I'm sorry. The only time I saw them more excited is when we were viewing one of the subway tunnels, and someone said, "Oh, I didn't know there were so many cats down in the subway system." They were not cats. This is really a unique design, a unique system. We will deploy it here, but as you heard, this could be a national model because it is a totally different way to reconstruct a tunnel. It's faster, it's cheaper, it's better than the way we have been doing it now. And New York should be the first. And we are trying to be the first. This state is the most aggressive state in building infrastructure in the United States of America. Period. Period. No one is doing the development that we are doing. Roads, bridges, airports. The corollary to that is, let us be the state that is leading in innovation and new designs and new technology. And that's exactly what this does. This fiberglass wrapping of the bench wall, this has never been done before. I coincidentally heard about it because we had an issue with the old Tappan Zee Bridge, which was unstable, and one of the engineers recommended a fiberglass wrap to literally hold the bridge together. That's how powerful this is. The fiber optic sensors, yes, they can detect movement in the bench wall. I'm interested in them for different applications. You can tell when a worker is in that tunnel. By the way, you could tell when someone who is walking into that tunnel who doesn't belong in that tunnel and may be violating security or posing a security risk is in that tunnel. So this technology not only works for this situation, but has capacities well beyond. With that, let me turn it over to Chairman for
Thank you, Governor Cuomo, for bringing us together today and helping to assemble what I consider, and is unquestionably, world-class team from premier engineering schools at both Columbia and Cornell. To the deans, thank you for outstanding efforts researching and engineering a new approach to a critically important project for New York City. To our MTA team for refusing the temptation of being held captive to the way we've always done things, but open to new ways of doing things, better ways of doing things, and keeping forefront in our minds the reason why we're all here, the riding public. We're grateful to all of you for your help in reviewing the plans for the L train. As we take a fresh look at the L train project, we work very closely with these experts. The objective was to minimize the impact on our customers while achieving the goals of the project, to repair the L train tunnel and make it more resilient against future storms. After reviewing the proposals of the expert review team, we were thrilled that they had developed an innovative and more efficient approach, which the MTA is adopting. Based on these recommendations, we will not be shutting down the tunnel, and no full closure of service between Manhattan and Brooklyn will be necessary. No apocalypse. Instead, we'll conduct all repairs on nights and weekends, and we'll only need to close one tube at a time for repairs, allowing the second tube to run trains in both directions. Weekday and rush hour schedules will be unaffected. On nights and weekends, the L train will be running with 15 to 20-minute headways, which is no different from the current overnight service. We expect that these repairs will take between 15 and 20 months, depending on how much bench wall will need to be removed. So you might ask, well, why wasn't this approach considered earlier? The answer is that the integration of these approaches, and there are several, and the technology has not been previously applied in the context of a rehabilitation project underground. It's innovative, creative, and we deem it a sound plan. In addition, I want to make clear that despite this positive development, there remains the potential to impact our customers on weekends, which is why we still plan to implement additional subway service where it's needed, such as on the G and M lines and the 7 line. Is obviously a major shift in approach. We'll continue to work closely with local communities, the City of New York, and all of our stakeholders, and solicit their input throughout, but without a doubt, this is a less invasive, more efficient approach to rebuilding the L train tunnel for the future, and it represents a huge win for our transit system and our customers, and for that, we can all celebrate and be thankful. So thank you all. Thank you, Governor.
Well said. Thank you.